Today's goal is to evaluate limits. Let's start by looking at the graph of a function. If this is our function f of x, we can evaluate left and right-handed limits by looking at the function and looking to see, for example, what y value does the function approach, limit means gets really close to, as the x value gets close to, arrow means approaches, -2 from the left-hand side. If I put what appears to be an exponent of a negative sign, that means I'm coming not on the left side of the graph. It is not the green arrow, but meaning, not moving to the left, but coming somewhere to the left of -2. So I'm looking at this blue arrow. In this case, both the blue and the green arrows approach the y value of 3, so the left and the right-handed limits would both be 3. But if we're looking at the left and the right-handed limits as x approaches 1, now they're different. For example, the limit of f of x as x approaches 1 from the right, this means I need to move on the right side of 1. This approaches the y value 4. Whereas the limit of f of x as x approaches 1 from the left, here I'm on the left side of 1, getting closer and closer and closer to the y value, -3. Because the right-handed limit and the left-handed limit are not the same, that is, because the function approaches a different y value if you come from the right side of 1 than if you come from the left side of 1, that's why we would say that the limit of the function as x approaches 1 does not exist. That's saying the two-sided limit, meaning coming from the left and coming from the right, does not exist. Whereas the two-sided limit of f of x as x approaches -2, coming either from the left side or the right side, in either case you're approaching the y value 3. Now I chose -2 and 1 to focus on because these are places where the function value is different from the limit. The function value is asking what actually is the y value when x is 1. In this case I'm pointing here because you have to look for the closed circle. So f of 1 is 2. The y value of the function at the x value 1 is 2, even though you're approaching, getting really close to different y values. A few more examples to consider. The limit of the function as x approaches 4 does not exist because the function has a vertical asymptote at x equals 4. That is, the y value does not approach one single value as the x values get closer and closer to 4, either from the left-hand side or from the right. The y values continue going up, 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 or down. Because they don't approach one single number, we say the limit does not exist. As a final example, if there's a closed or an open circle at x equals 6, we would say that the two-sided limit of the function as x approaches 6 does not exist. Since there is no function to the right of 6, there can't be a right-handed limit. You're not getting close to any value because there are no values. Therefore, the left-handed limit and the right-handed limit can't be equal. If the left and the right-handed limit are not the same, then the two-sided limit does not exist. Let's take a look at some non-graphic problems where we'll need an algebraic approach. First, take a look at number 1. Whenever possible, you should try substitution first. Sometimes it's a quick and an easy way to get an answer. Sometimes it doesn't work. But we'll get to that shortly. Number 1 says the limit of f of x, we're calling this our function, of x plus 1 over square root x plus 1 as x approaches 1. Well, if we substitute, we see that the limit is just 2. If we substitute in problem 2, then we get that the limit is 1 minus 1 over square root 1 minus 1. That gives us 0 over 0. This is called indeterminate over 0, we say it's undefined, because we just can't divide by 0. But if you get 0 over 0, we say it's indeterminate form. That means you cannot, that's what in means, determine whether or not a limit exists. Anytime you get an answer in indeterminate form, you need to try a new strategy. If you see a radical expression, sometimes a nice strategy is to multiply by the conjugate, spell it out for you, of the radical expression. That is, keep the first term and take the opposite of the second term. In this case, we'll multiply by the conjugate of the radical expression. Doesn't matter if it's in the numerator or the denominator. So we'll multiply by root x plus 1. I kept root x the same. I took the opposite of -1. When you use the box method in the denominator, something really nice happens. You get root x times root x is just x, minus square root of x plus square root of x. These will cancel out, -1. I could use the box method in the numerator, but I'm not going to because it would get kind of messy. How nice is that? My x minus 1's cancel out. I get the limit as x approaches 1 of root x plus 1, and now I can just substitute. I get square root 1 plus 1 is 2. So again, indeterminate form didn't tell us whether or not the limit existed. It just said, you're going to need a new strategy, such as multiplying by the conjugate of the radical expression. Let's take a look at number 3. I always want to try substitution first. It can be quick and easy if it works. I get 1/4 minus 1/4 over 0. Ooh, that's 0 over 0. Again, I'm in indeterminate form, and therefore I need to try a new strategy. I don't see a radical expression, so multiplying by the conjugate isn't appropriate here. It's not going to help. If I see fractions within fractions, one trick that sometimes works is to reduce to one fraction. That is, I've got this 1 over 4 plus x minus 1/4. Let's get these together and turn this whole expression into one single fraction. I can do so by obtaining a common denominator. We get 4 over 4 times x plus 4 minus x plus 4 over 4 times x plus 4 equals 4 minus x minus 4. You need to distribute that subtraction over 4 times the quantity x plus 4. My 4's cancel out. I get negative x over 4 times the quantity x plus 4. Okay, so that means if I'm looking back at the limit, it's the limit of, I took this whole numerator and reduced it down to negative x over 4 times the quantity x plus 4. It's still over x, just like here, as x approaches 0. Now my strategy was to reduce to one fraction. I can interpret this fraction bar as meaning division. Well, we know how to divide by fractions. You just multiply by the reciprocal. So I keep the first fraction the same. I take this second fraction, x over 1, and I flip it to 1 over x. Now I'm no longer dividing, I'm multiplying. This is nice, my x's will cancel. I get the limit as x approaches 0 of negative 1 over 4 times the quantity x plus 4. Let's try substituting. You get negative 1 over 4 times 4. Oh, my limit is just negative 1/16. Okay, let's look at a few others. Here, next up, we've got the limit of the log of x as x approaches 1,000. As always, I try substituting first. You get the log of 1,000. Well, log, oh yeah, that's the inverse of 10 to a power. Oh, 1,000 we can write as 10 cubed. These are inverses, they cancel out. We just get 3. Similarly, if we substitute in example 5, you get the log of 1/10. Ooh, but I'd like to write that as a power of 10. Oh yeah, this would be the log of, don't want you to miss this. You have 10 or 10 to the first in the denominator. You can bring it up to the numerator with a negative exponent. 10 to the negative 1 is the same thing as 1/10. Now my inverse functions cancel out and I get negative 1. Alright, just a few more log facts for you. Now we have the limit of the log of x as x approaches negative 1/10. Let's try substituting. this would be the log of -1 times 10 to the -1. I can't cancel these out because then I still have this -1 to deal with. Well, if I'm not sure what to do with that, I remember log is the inverse function of 10 to a power. So maybe remembering 10 to the x looks like this. We would have points like 0, 10 to the 0 is 1, 10 to the 0 is 10, 2, 10 to the 0 is 100, -1, 10 to the -1, remember that's 1/10, -2, 10 to the -2, keep in mind that's 1/10 squared, so that's 1/100th. So this is y equals 10 to the x. Its inverse function, y inverse, would have points like 1/100th, -2, 1/10th, -1, and taking the x and y values and switching them. It doesn't seem like I can get to x values that are negative. I'm getting x values that are closer and closer and closer to 0, right? This would be 0.1, 0.01, and so on. But it doesn't seem like you can input a negative number into the log function. So this limit does not exist. Okay, just a few more. 7 is different from the other ones we've looked at so far because it's asking us the limit as x approaches infinity. That means as you move all the way to the right of the function, what is the y value doing? Well, if we look here, these y values are getting bigger and bigger and bigger. They're approaching infinity as x approaches infinity. Because it's not approaching one single y value, we say the limit does not exist. But if it's a rational function we're looking at, sometimes they have horizontal asymptotes. That is, if you're looking at this function, and it's got a horizontal asymptote here. If we call this guy f of x, the limit of f of x as x approaches infinity would be 0. Because it's getting really close to this horizontal asymptote at y equals 0. Well, the way this function is written, we have to compare the degree of the numerator and the degree of the denominator. Because the degree of the numerator is larger than the degree of the denominator, the function does not have a horizontal asymptote. Maybe it looks something like this. You don't have to know this offhand. But it doesn't approach one single y value. The y values maybe keep increasing, or maybe they keep decreasing. In either case, because it's not approaching one y value as a horizontal asymptote, we say the limit does not exist. Now, if I took this function, and instead of having an x cubed up top, it had just an x squared, plus some other terms, and that -4x squared in the denominator, in this case, as you go all the way to the right, these y values are increasing about at the same rate, so we look at the ratios of leading coefficients. This function has a horizontal asymptote at -1/4, which means the y values get really close to -1/4 as x approaches infinity. There's only one other case for rational functions. If the degree in the denominator is greater than the degree in the numerator, then the function as a whole is going to have a horizontal asymptote at 0, just like this one. So this function would have limit 0 because the function approaches the horizontal asymptote at y equals 0.